Now we are moving into the next big idea in physics, energy. So we have finished talking about work, force acting through a distance. But what happens to the object when work is done on it? That's where energy comes in. Now take a moment and think, when you push something and it speeds up, or when you lift something and it gains height, what's actually changing? Think about one everyday example where you notice energy changing. And let's connect this to our crate example. So when we applied a force, Newton's law tells us it accelerated. Its velocity increased. That means we are doing work because the force is acted over a distance. And here's the key idea. Doing work on an object increases its energy. The specific energy associated with motion is called kinetic energy. And according to work energy theorem, the work done on an object equals the change in its kinetic energy if we ignore other losses like friction. And the equation for kinetic energy is half mv square. Right? Kinetic energy, Ke means kinetic energy. So here m is the mass of the object and v is its speed. So since this is an energy, its units are joules. Now for example, if the crate starts at rest, then its kinetic energy is 0 because velocity is 0, right? If this is 0, then kinetic energy is 0. So if the crate starts at rest, then its initial kinetic energy is 0. As we apply a force and it moves a distance d, then it gains a kinetic energy of half mv square, which is equal to the work done on it, right? So if the crate was already moving, then the increase in its kinetic energy would still equal the work done. Therefore, work done W is equal to change in kinetic energy. Here delta Ke means change in kinetic energy. That means final kinetic energy minus initial kinetic energy. And if the crate starts at rest, then its initial kinetic energy is 0. But if it was already moving, then we have to consider its initial kinetic energy when we are calculating the work done. Now let's look at what happens when kinetic energy decreases with time. Imagine a moving car. When you apply the brakes, the car skids to stop. That means its final velocity is 0. If velocity is 0, then the final kinetic energy is also 0. Kinetic energy final is 0, right? Because velocity is 0. So the car has lost kinetic energy, right? So the change in kinetic energy here is negative. Change in kinetic energy means final kinetic energy minus initial kinetic energy. And the final kinetic energy is 0. Therefore, we get a negative value for the change in kinetic energy. And that means the work done on the car is also negative, right? Now think about this. Why does the car stop at all? What force is acting? So when you brake, the frictional force acts on the car in the opposites to its motion. Because the force is opposite to the displacement, the work done by friction is negative work, remember? So negative work means the force is removing energy from the system rather than increasing it. So that means negative work is the work done by a force acting in direction opposite to the object's motion, right? Now let's put these ideas on kinetic energy into practice with a simple calculation on kinetic energy. A 120 kilogram crate starts from rest on a frictionless floor. So if you apply a net force of 96 Newton for 4 seconds, the crate reaches the final speed of 3.2 meters per second after moving a distance of 6.4 meters. And we want to find the work done on the crate, and the final kinetic energy of the crate. Now before I solve it for you, I want you to pause the video here and give it a try on your own. Use the equations for work and kinetic energy we just discussed. When you are ready, hit play again to check your solutions. Now we are applying 96 Newton force for a time of 4 seconds. And this results a final speed of 3.2 meters per second. So the V final is 3.2 meters per second, and the crate moves a distance of 6.4 meters, and its initial speed is 0 because it starts from rest. Now you are asked to find the work done on the crate and the final kinetic energy of the crate. Now these are the parameters given. The force 96 Newton and the distance 6.4 meters. So can you calculate the work? Work is just the force times distance, right? F times D. Now here force is 96 Newton and distance is 6.4 meters. Therefore work done is 614 Newton meter, or it is 614 joules. 1 Newton meter is 1 joules. Now for part B, we have been given the mass of the crate, which is 120 kilogram, and final speed, it is 3.2 meters per second. And you are asked to find the final kinetic energy of the crate. So let's find the final kinetic energy. So what is the equation? Kinetic energy, final kinetic energy is half mass times v square, and v is the final velocity, and final velocity is 3.2 meters per second, right? Half mass is 120 kilogram and velocity is 3.2 meters per second. Take the square value. Therefore kinetic energy is 614 Newton meter, or 614 joules. So did your answers match? Notice how the work done equals the final kinetic energy. So here work done equals to final kinetic energy. Why? Remember the work energy theorem? Work done is equal to change in kinetic energy, final kinetic energy minus initial kinetic energy. And here initial kinetic energy is 0 because it starts from rest. Velocity is 0. Therefore, work is equal to final kinetic energy for this specific problem, right? So that's the work energy theorem at work. Now so far in this section we have learned about kinetic energy, the energy of motion. So it can be gained or lost, and the work done on an object equals the change in its kinetic energy. Next we will discuss another important form of energy, potential energy. So earlier we said that doing work increases an object's energy, and that the work done can equal the change in kinetic energy. But what if there is no change in kinetic energy? Where does the energy go? So in that case we say the object's potential energy has increased. So pause here for a moment and think, how is potential energy different from kinetic energy? Let's look at an example. Imagine lifting a crate in a loading dock as shown in this figure. So to pull the crate upward, you should apply a force, and at the same time the crate experiences a downward gravitational force W, which is equal to mg. So if your pulling force exactly equals the gravitational force, then the net force is 0. If F equals W, then net force is 0. That means the crate moves upward at a constant velocity. So its kinetic energy doesn't change. If the velocity is constant, v is not changing, that means kinetic energy is not changing since the speed is same. So final speed equal to initial speed. That means no change in kinetic energy. So where does the work you did go? It increases the crate's potential energy. So in this case it's gravitational potential energy. So work done in here is equal to change in potential energy. So change means final minus initial. So the work done is equal to final potential energy minus the initial potential energy. Now what is the potential energy equation? Potential energy is equal to mgh. M is the mass, g is the gravitational acceleration, and h is the vertical distance the crate lifted. Vertical distance, that is h. And this is called gravitational potential energy. So we are doing work against gravity. So since this is energy, the units are joules. Now imagine letting go of the rope. What happens to the crate? It accelerates downward, and the potential energy it had is converted into kinetic energy. So the term potential energy literally means energy that is stored to be used later for other purposes. So think back to our crate example. When we lift the crate, its height increases and it gains gravitational potential energy. So at this point, the crate has gravitational potential energy of mgh, right? And when we let go of the rope, the crate accelerates downward, right? And it gains kinetic energy. So now the initial potential energy has now been converted into kinetic energy. This energy has now converted into kinetic energy. And the key characteristic of potential energy is that it depends on the position of the object. Change the position and the potential energy changes. So before we move on, pause the video and think. Can you name one real example where energy is stored as potential energy and then converted to kinetic energy? Okay, now let's apply this idea in a simple exercise to calculate potential energy and see it in action. A crate with mass of 100 kg is lifted onto a loading dock with 2 meters above the ground. So now the loading dock is 2 meters. Height is 2 meters above the ground. Now we have the crate on the loading dock. Now how much gravitational potential energy has it gained? So before I solve it for you, pause the video and give it a try on your own. Use the equation for gravitational potential energy, which is equal to mgh. And m is the mass, g is the gravitational acceleration, which is 9.8 meters per second square, and h is the height. So once you have the answer, continue playing to check it. Now we know mass is 100 kg and height is 2 meters, right? So what is potential energy then? Potential energy is mgh. And here m is the mass of the crate, which is 100 kg. G is gravitational acceleration, which is 9.8 meters per second square, and h is 2 meter. Therefore potential energy is 980 Newton times 2 meter, which is 1960 Newton meter, or it is 1960 joules. So the crate has gained 1960 joules of gravitational potential energy, right? After it was moved 2 meter height. Now think about it. If we let go of the crate, this 1960 joule of potential energy would convert into kinetic energy as the crate falls. So this shows the direct link between potential and kinetic energy. Now here's a new scenario. Work is done on a large crate to tilt it so that it balances on one edge rather than sitting flat on the floor as it was initially. Now the question, has the potential energy of the crate increased? Now take a moment and think. Tilt in the crate changes its center of mass. So does this involve an increase in height compared to its original position? So the correct answer is A. Yes. So even though the crate is not being lifted straight up, the center of mass of the crate rises when it tilts. Since gravitational potential energy depends on height, the potential energy has now increased. And if it is released, it will fall back and convert the potential energy into kinetic energy. Now that we have covered gravitational potential energy, let's look at another type of stored energy, elastic potential energy. Now, elastic potential energy occurs when you stretch or compress an object, like a spring or a rubber band. Now, imagine a spring attached to a post with a wooden block attached to the other end of the spring, as in this figure. So, if we pull the block from its original unstretched position, then we do work on the spring. So, the block gains energy, and this is called elastic potential energy. And if we let go of the block, it will fly back, right? Converting this stored energy into motion. So elastic potential energy is the energy gained when work is done to a stretched or compressed spring. Now take a moment and think. Can you name some everyday objects where elastic potential energy is at work? Think about it, okay? Now let's figure out how to calculate the elastic potential energy of a spring. Here, the force exerted on the spring is proportional to the stretch distance. F is proportional to stretch distance x. So we can write the equation for this force as F equals minus kx. And the k is the proportionality constant, or in this case we call it as spring constant, and it depends on the stiffness of the spring. And F is the force exerted by the string, and x is the distance the spring is stretched, which can be measured from its original unstretched position. So if this is the original unstretched position, then x is this distance. Okay, so this is called Hooke's law. You might notice the minus sign. Pause for a moment and think, why is there a minus sign? The minus sign shows that the spring is always pushes or pulls back opposite to the direction of displacement. So if you stretch it to the right, then it pulls to left. So F is equal to minus kx. The direction of F and x are opposite. So if you stretch it to the right, it pulls left, and if you compress it, it pushes right. So the force is always in the opposite direction to the displacement. Now what about elastic potential energy? Well, the energy stored in the spring is the work done on it. And work is force times distance. But here the force changes as the spring stretches. The force is not constant, force is changing constantly. Therefore, we have to take the average force. So if we plot force versus displacement, we can find the average force. So average value is final minus initial over 2. Therefore, average force is equal to half kx. Okay, kx minus 0 over 2, which is half kx. So the elastic potential energy is the average force times the distance, which is equal to half kx force, and the distance is x. Therefore, it is half kx square. So this formula works whether the spring is stretched or compressed. So this is the elastic potential energy equation, which is equal to half kx square. So gravitational potential energy and elastic potential energy are two different types of energy. Gravitational potential energy is equal to mgh and elastic potential energy equals to half kx square. Notice the difference, okay? Now let's pause a moment and think. If we double the displacement, what happens to the elastic potential energy? If the x is double, then we have to take the square value, right? PE is equal to half k 2x square, which is 4x square. So that means if the displacement is double, then its elastic potential energy increases by 4 times. Now the key idea is the more you stretch or compress a spring, more energy is stored in it. Now before we move into the next section, let's talk about conservative forces. Remember the crate we lifted to learn about gravitational potential energy. So when we let go, it accelerates downwards. As it falls, it loses potential energy and gain kinetic energy. And the same idea applies to a string. So if we let go of a stretched or compressed spring, it loses elastic potential energy and the block gains kinetic energy. So the important point here is that these energies, gravitational potential energy and elastic potential energy, can be completely recovered and used again in other forms. That's why the forces associated with these energies like gravity and elastic force are called conservative forces. Now here's the key definition. Conservative forces are forces for which the energy can be completely recovered. So when work is done against a conservative force, the energy gained by the system can later be fully recovered as other forms of energy, like converting potential energy into kinetic energy. Now what about friction? Is it a conservative force? Think about braking a car. The friction force converts the car's kinetic energy into heat, which leaves the system or increases the internal energy. So the energy is not converted back into potential energy and cannot be fully recovered. Therefore, friction is not a conservative force. Now to summarize, if energy can convert completely between kinetic and potential forms, the force is conservative, like gravity and elastic forces. If not, like friction, the force is non-conservative. So this idea leads us naturally to our next topic, energy conservation, which we will discuss in the next section of this chapter.